There's an object floating in our galaxy right now that is 20 billion times heavier than our Sun, and light itself cannot escape its surface. That's not the biggest one we know about. And it's not even close to the strangest kind of black hole out there. Some of them are the size of an atom. One might be sitting a light year from Earth undetected. By the end of this video, you'll know exactly which kind should scare you most. A black hole isn't a hole. It's not empty space. It's the opposite. It's matter packed so densely that its gravity bends the fabric of space and time back on itself, creating a boundary called an event horizon past which nothing, not even light, can climb back out. Albert Einstein's equations predicted them in 1915. Einstein himself didn't believe they could actually exist in nature. He was wrong. We've now directly photographed two of them, detected the gravitational ripples from hundreds of them colliding, and mapped out at least 6 genuinely different categories of black hole, each one stranger than the last. The most ordinary kind of black hole in the universe starts its life as a very extraordinary kind of star. When a star roughly 20 times more massive than our Sun runs out of fuel, it can no longer produce enough outward pressure to fight its own gravity. The core collapses in less than a second. What follows is a supernova, one of the brightest explosions in the universe, and at the very center of that explosion, if the leftover core is heavy enough, it doesn't stop collapsing. It keeps shrinking past the point where any known force can stop it, crushing down into a single point. These are called stellar mass black holes, and they typically weigh somewhere between about 5 and 100 times the mass of our Sun, squeezed into a region only a few kilometers across. The nearest confirmed one to Earth, called Gaia BH1, sits roughly 1,560 light-years away, close, on a cosmic scale, but still utterly unreachable. But here's the part that should unsettle you. Astronomers estimate there could be 100 million stellar mass black holes scattered across our galaxy alone, and we've only directly confirmed a few dozen of them. Most are invisible unless they're actively feeding on a nearby star, because a black hole with nothing nearby to pull in gives off no light at all. It's just there, silent, waiting. Every large galaxy in the observable universe, including our own Milky Way, appears to have one of these sitting at its exact center. Supermassive black holes range from hundreds of thousands to tens of billions of times the mass of our Sun. Our galaxy's own supermassive black hole is called Sagittarius A*, weighing in at roughly 4.3 million solar masses. In 2022, the Event Horizon Telescope team released the first ever direct image of it, a faint orange ring of superheated gas glowing around an absolute void at the center. But Sagittarius A* is practically a lightweight compared to what's sitting in the galaxy M87. That black hole, the first ever directly photographed back in 2019, weighs an estimated 6.5 billion solar masses. And the current record holder, a black hole called TON 618, is estimated at roughly 66 billion solar masses, so large that its event horizon alone would swallow our entire solar system and keep going for hundreds of times that distance. Nobody fully agrees on how objects this large formed so early in the universe's history. Some formed within the first billion years after the Big Bang, which shouldn't have been enough time for a normal star to collapse and then grow that massive through feeding alone. It's one of astrophysics' biggest unsolved puzzles. So far we've covered the small ones born from dying stars, and the monstrous ones anchoring entire galaxies. But there's a size gap between them that shouldn't exist, and for decades, scientists couldn't find a single black hole to fill it. For a long time, this category was almost theoretical. Astronomers had stellar mass black holes on one end and supermassive ones on the other, but nothing convincingly in between, weighing somewhere in the hundreds to hundreds of thousands of solar masses. That gap was a real problem, because most models of how supermassive black holes form require something in the middle to grow from. Then, in 2020, gravitational wave detectors caught something that shouldn't have been possible. Two black holes, 66 and 85 solar masses respectively, sizes that fall inside a range physics says shouldn't even be able to form from a normal collapsing star, collided and merged into a new black hole weighing about 142 solar masses. That merger, named GW190521, produced the first confirmed intermediate mass black hole ever directly detected. It solved one mystery and opened another. If these black holes can't form the normal way, how many hidden ones like it are already out there, invisible, waiting for their next collision to give them away. Every black hole we've covered so far needed a star to form first. Primordial black holes didn't. They're a purely theoretical category, never confirmed to exist, that some physicists believe formed in the first fraction of a second after the Big Bang itself, before stars existed at all, out of extremely dense pockets of the early universe collapsing directly under their own gravity. And here's the unsettling part. If they exist, some of them could be smaller than a single atom, while weighing as much as a mountain. Because they didn't need to reach a stellar mass threshold to form, primordial black holes could theoretically exist at almost any size, from microscopic to massive. Some scientists have proposed that primordial black holes might even make up a portion of dark matter, the mysterious, invisible substance that makes up roughly 27% of the universe's total mass-energy content but has never been directly observed. If that theory is ever confirmed, it would mean some of the missing mass holding galaxies together isn't exotic particles at all. It's black holes, quietly drifting through space, undetected, since almost the beginning of time. We've now covered 4 categories by size: stellar, supermassive, intermediate, and primordial. But size isn't the only way black holes differ from each other. Some of the strangest ones aren't defined by how big they are. They're defined by how they move, and what happens to anything that gets too close. Most real black holes in the universe aren't standing still. They spin, some of them extraordinarily fast, a leftover of the rotation of the star that collapsed to form them. These are called Kerr black holes, named after physicist Roy Kerr, who solved Einstein's equations for a rotating mass back in 1963. Some of them spin close to the theoretical maximum speed physics allows, dragging the fabric of space and time around with them like a whirlpool. This effect is called frame dragging, and it means the space immediately outside a rapidly spinning black hole is being physically twisted around in the direction of the spin, so much so that even light itself gets pulled along with the rotation before it can escape. A black hole candidate called GRS 1915+105 has been measured spinning at close to 1,150 times per second. To put that in perspective, that's faster than a kitchen blender, on an object several times the mass of our Sun. This next type is almost entirely theoretical in practice, because the universe tends not to let it happen, but mathematically, it's real, and it's genuinely strange. A charged black hole carries electric charge in addition to mass, distorting spacetime differently than an uncharged one. In theory, if a charged black hole's charge got large enough relative to its mass, its event horizon could disappear entirely, exposing something physicists call a naked singularity. A singularity is the infinitely dense point at a black hole's core. Normally it's hidden forever behind the event horizon, a cosmic censorship that keeps our physics from breaking down where we can actually observe it. A naked singularity would violate what physicists call the cosmic censorship hypothesis, a rule most scientists believe the universe enforces specifically to prevent an infinitely dense point of undefined physics from being directly visible. In practice, black holes gain charge only briefly before nearby matter neutralizes it, so a stable charged black hole likely can't survive in the real universe. But the math says it's possible. And that's exactly the kind of possibility that keeps theoretical physicists up at night. So far, everything we've covered actually forms, has been detected, or is at least mathematically consistent with our universe. What comes next gets a lot more speculative, and a lot more unsettling. Micro-black holes are a hypothetical class so small that some versions could theoretically weigh less than a paperclip while being smaller than a single proton. Some physicists have proposed they could form briefly in extremely high-energy particle collisions. When the Large Hadron Collider switched on in 2008, this exact possibility triggered a wave of public panic. Some people genuinely worried scientists might accidentally create a micro-black hole that could swallow the Earth. It didn't happen, and physicists explained at the time why it couldn't. Any micro-black hole created in a particle collision, if it formed at all, would be so small and unstable that it would evaporate in a fraction of a second through a process called Hawking radiation, losing mass and energy faster than it could pull anything else in. Stephen Hawking proposed in 1974 that black holes aren't entirely black. They slowly leak radiation and lose mass over time, and the smaller the black hole, the faster it evaporates. A micro-black hole wouldn't have time to do anything except disappear. Not every black hole stays where it formed. Some get kicked out of their host system entirely, flung through space at incredible speeds after an asymmetric supernova explosion or a violent gravitational interaction with other massive objects. In 2022, astronomers announced they had found direct evidence of one of these. A rogue black hole drifting through interstellar space completely alone, roughly 5,000 light-years from Earth, detected only because its gravity was bending the light of a distant star behind it. That detection method is called gravitational microlensing, and it's essentially the only way to find a rogue black hole, because with no companion star to feed on and no matter swirling around it, a lone black hole in the dark gives off literally zero light. Estimates suggest our galaxy alone could contain tens of millions of these solitary wanderers, and short of one drifting directly in front of a background star at the exact moment we're watching, we would have absolutely no way of knowing it was there. Small ones, giant ones, spinning ones, electric ones, microscopic ones, and invisible wandering ones. Now we get to the part of this video that isn't really about types of black holes anymore. It's about what black holes actually do to reality itself. Sometimes two black holes end up orbiting each other, spiraling closer over millions or billions of years until they finally collide and merge into one. These collisions are so violent they don't just release energy as light. They release energy as literal ripples in spacetime itself, called gravitational waves. On September 14, 2015, humanity detected one of these ripples for the very first time, and the collision that caused it had happened 1.3 billion years earlier, on the other side of the universe. That event, known as GW 150914, came from two black holes weighing 29 and 36 solar masses merging into one, releasing more energy in a fraction of a second than every star in the observable universe combined radiates in that same instant, all of it as gravitational waves, not light. The detectors that caught it, called LIGO, measured a distortion in spacetime smaller than 1/10,000th the width of a proton. It won the 2017 Nobel Prize in Physics, and it opened an entirely new way of observing the universe, one that doesn't rely on light at all. This next part isn't a category of black hole. It's what every single category above would do to you, physically, if you got close enough, and it's one of the most genuinely horrifying things predicted by physics. As you fall feet first toward a black hole, the gravitational pull on your feet becomes so much stronger than the pull on your head that your entire body gets stretched, pulled apart, atom by atom, into an impossibly long thin strand of matter. Physicists actually call this process spaghettification, a real scientific term. Near a stellar mass black hole, this would happen almost instantly and violently, tearing a human body apart within a fraction of a second while still outside the event horizon. Strangely, near a supermassive black hole, the math works differently. The tidal forces stretch out over such a vast area that a person could theoretically cross the event horizon of something like Sagittarius A** completely intact, alive, with no physical sensation of anything unusual happening at all. They just wouldn't be able to come back. Ever. Here's a question that has genuinely divided some of the smartest physicists alive for 50 years. When something falls into a black hole, is the information about what it was, its exact atomic structure, its full physical history, destroyed forever, or does it somehow survive? Stephen Hawking spent decades insisting the information was lost forever. Then, in 2004, he stood up at a physics conference and publicly admitted he'd been wrong. The problem is this. Quantum physics has a fundamental rule that information can never truly be destroyed, only transformed. But general relativity predicts that anything crossing an event horizon is gone, permanently, with no way to reconstruct what it was from the outside. Combined with Hawking radiation slowly evaporating a black hole down to nothing over unimaginable timescales, you get a genuine contradiction between two of physics' most trusted theories, one that still isn't fully resolved today. It's called the black hole information paradox, and it's considered one of the biggest open problems in all of theoretical physics. Every black hole in this video, no matter how massive, is theoretically going to die. Because of Hawking radiation, black holes very slowly lose mass over unfathomably long timescales, and the more massive the black hole, the longer it takes. A stellar mass black hole would take roughly 10 to the power of 67 years to fully evaporate. A supermassive black hole like the one at the center of our galaxy would take closer to 10 to the power of 100 years. For comparison, the universe itself is currently about 13.8 billion years old, 1.38 times 10 to the power of 10. These evaporation timescales are so far beyond that number that the digits themselves stop feeling real. But physicists have actually calculated what the very end of that process looks like. And it's the strangest and most violent moment in this entire video. As a black hole shrinks down to its final moments, Hawking radiation accelerates dramatically. In its last fraction of a second, a black hole that has existed for longer than any star, any galaxy, any structure the universe has ever produced, releases the rest of its remaining mass in one final burst, theoretically detonating with the energy of millions of nuclear weapons, all at once, in complete darkness, with almost certainly nothing left in the universe old enough or close enough to ever witness it. Every black hole that has ever existed or will ever exist is, on a long enough timeline, a slow-motion bomb with a fuse longer than the current age of the universe repeated 10 billion trillion 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 times over. Every kind of black hole in this video, the common ones, the monstrous ones, the spinning ones, the theoretical ones, shares the exact same ending. Total, silent evaporation. So far in the future that the concept of future barely applies anymore. We built our entire understanding of the universe's biggest objects, and it turns out every single one of them is temporary. If the idea of a black hole existing 5,000 light-years away right now, completely undetectable, freaked you out a little, you'll want to see our next one. What's actually inside a black hole, according to physics? Which kind from this video sounds the scariest to you? The rogue ones we can't see, or the supermassive ones anchoring entire galaxies? Drop it in the comments, and subscribe. We go deeper into space every week.